Apologize for that break. Going back, we're gonna pick up right where we left off. So, what ends up happening sometimes is Cisco will turn off my recording mid-recording if nobody's watching it. And so, that's what it did. And I didn't even notice until I was done going through all of this. So bear with me. It was awful. It was like a kick in the balls. Okay. So anyways, we figured this out. We said it was our observed minus our expected squared, right? Divided by our expected, and then we hit enter and we get 0.06667. All right, so that's where that number comes from. And that's our chi-squared for our purple stems. And remember, we're gonna add up these chi-squareds in just a second. So the next one's same thing. So we're gonna go equals, give me two parentheses facing the same direction. And we'll take our observed minus our expected, close one of those parentheses, shift 6, so exponent 2, close parentheses, backslash, or divided by, and then we will click on our expected and then hit enter, 0.2. And so that's my chi-squared for my green stems. And then finally, so we're going to go back to our assignment here. All right, so we're back on our paper. And what we can see here is, so anyways, we took the expected, subtracted it from observed, squared it, divided by expected for both categories. And so what I did here is for the purple stems, we got 0.067, as you see here, right? 0.06, and then I just rounded up so we didn't have a bunch of decimals. And then we did the same for green stems, and we got 0.2. And then now we take those two numbers and we add them together to get our chi-squared statistic. So we just took 0.067, added 0.2 to it, and I got 0.267. So I'm going to do that over here, and I'm just going to say equals the sum, open bracket, and then I'll say of these two numbers added together. I get 0.26667. Okay, and that's our chi-squared. That's the number that we're looking for. Alrighty, going back to our lab. So we can explain this chi-squared statistic as being the differences between observed and expected values for each group squared and divided by the expected value for each group. And so this return value, the chi-squared, is used in conjunction with something called degrees of freedom, and then also like our chi-square distribution table, so a probability field that tells us what the probability is that our model is accurate. So what you can do is, let's do a thought experiment here. If our observed values are way different than our expected values, this number is going to be big on top in the numerator, and then we square it, and then we divide it by our expected. And so the bigger the difference between what we observe and what we expect to observe, like what we observe and what we expect to see, if that difference is big, then this chi statistic is going to be very large. And so keep that in mind, and that's going to play a big role in whether or not we reject our model or not. All right, the second data point we need is the degrees of freedom. There's a simple formula for degrees of freedom, which is taking the number of categories and then subtracting 1 from that number of categories, okay? So let's do that real quick. All right, sorry, I had to tell my kid to shut up. Politely, of course. All right, so the number of categories, subtract 1. So the number of categories we have is just 2. They're either green stems or they're blue stems. So we have 2 categories, subtract 1 from that, and we get 1 for our degree of freedom. Now, degrees of freedom is something that's you're going to see in statistics a lot. A good way to think about it is like this, okay? Consider that you have 100 M&Ms. And let's say that I have red, yellow, and blue M&Ms, okay, in that 100 M&Ms. And they're all mixed up, okay? I know I have 100 total, but I have red, yellow, and blue. How many categories, if I know the number value, the numerical value for the number of those categories, like let's say if I know the number of red M&Ms and I know the number of yellow M&Ms, how many categories do I need to know before I can determine the last category, before the last category is determined for me, I should say. So think about this. If I have red, yellow, and blue, let's say I have 10 red M&Ms and 50 yellow M&Ms. I have 100 M&Ms total. Okay, so if I have 50 yellow, or if I have 10 red, 50 yellow, then I have 60 M&Ms that are red and yellow. How many M&Ms are blue? 40. It has to be 40. So if I know the value of 2 of my groups, then the third group is already determined for me. And so we can, that's why there's the number of groups minus one. So if I have two groups like green and purple stems, and if I count 10 plants and five of them are green, I have to know that the other five are going to be purple. So I only have 1 degree of freedom. I only have one lane in which I can move the values, and then it determines the other lane. So I have two stem colors. If I know the total number of stems, which is in this case, whatever, 20 or something. If I know the total number of stems and I know the number of green stems, then I have to know the number of purple stems. So that's why I only have one, n minus 1 degrees of freedom. Okay, now we can use that chi-squared value that we determined earlier, right, that 0.267. We can use our degrees of freedom and we can figure out the p-value. You can calculate the p-value. So there's many ways to do this. You can do it in Excel. You can do it in a chi-distribution table like the one I have down here. Excel is more precise because it's mathematical, computer-based. This table is accurate, but not as precise because the values won't be as returned to you in a precise way. So it's just a matter of comfort and preference. But we can do it on both. So that's what we're actually going to do here. So we start at the degrees of freedom. We have 1 degree of freedom. We're going to trace our finger across this line, just across this row, until we reach the value, of our chi, which is the 0.267. So 0.267 is where I'm trying to fit 0.267 on this row somewhere. So 0.004, 0.016, 0.12, so that's a little less than 0.267, and then 0.455. Well, that's a little more then. So I know that my chi value fits somewhere between 0.12. I know it fits between 0.102 and between 0.455. 0.2, what was it? 0.267, right? That's going to fit right in there. Probably a little bit closer to, I don't know, maybe it's right in the middle actually. So my p-value is going to be determined from this top row up here. And the probability, so that's p-values, and we'll talk about those in a second. But my p-value, if my chi value is somewhere between these two, my p-value is going to be somewhere between those two numbers, 7.5 and 5.0. So p-value is probably 0.6, I'm guessing, somewhere in there. All right. All right, so our p-value is somewhere between that. So I give you an example here in this paragraph. I'm going to skip it because I just kind of went over that with you. P-values are a little bit complicated. So they're utilized in two different ways usually, and it depends on the experiment itself. The p-value itself is just the probability that the differences between the two groups are due to chance. So the two groups in our cases are observed and are expected. Now, don't get that confused with degrees of freedom. I know that it sounds weird, right, when we're talking about it now. But it's really just saying, okay, is the difference between our observations and our expected values, is that difference due to chance, or is it due to our model being erroneous, an erroneous model? In our case, we want the probability that it's an erroneous model to be very low. We want the chance that the model is accurate to be very high. In other cases, right, so that's the case where our case with this experiment is that we want a high p-value. We want our model, we want the differences that we see between observed and expected to be explained by chance. And so that's what the p-value is. That's the probability that the differences are explained by chance, by randomness, by random sampling. There are cases where you want the p-value to be very small, where the differences are not due to chance and that they are due to the differences between the two groups. This would be something like clinical trials for medications, like where one group gets a placebo, the other gets a treatment, and then whatever the effects of the placebo and treatment are, you want the effects to not be, you want the differences between the placebo and the treatment group, you want the differences to not be due to chance. Because otherwise you just wasted a crap ton of money on researching a chemical to do whatever it is that you want it to do, and it didn't work. That would suck. You want the differences between this placebo and the treatment group to be vastly different, so you can say, aha, look, the difference that I see in my treatment group, the probability that's due to chance is very low. So that p-value is very low. That the differences between the two groups is due to chance is very low in that case. And that's a good thing. So in the case of our modeling experiment, what was our p-value? Let's come up. Modeling experiment. What modeling experiment? Okay. In the case of this experiment, what was our p-value? So we said it was about 0.6 something, right? But what I'm going to do is come up here and I'm going to show you how to calculate it here. So let's type in degrees of freedom just so it's labeled on here. And degrees of freedom is 1. We know that. Now we need to figure out what our p-value is. So p-value of individual data. Because the individual data is slightly different than the class data. All right, so the p-value of individual data is, make sure I'm not getting shut out. Okay, good. P-value of individual data is equal to, so this is how you figure this out. We've got our two statistical values. So we've got 0.267 is our chi-squared. Degrees of freedom is 1. So we go equals, and we say, okay, Google Sheets, bring me up a chi, dist, a distribution table. And I'm going to start that. So it's equals. Don't forget the equal sign. I want the value of this cell to equal the chi distribution, and then I'm going to do open parentheses, and I'm going to click on 0.267, so the value in that cell, comma, no spaces, and then degrees of freedom, the value of that cell, and then I hit enter. And there you go. Look, it's 0.60. That's really close. So I'm going to come back here to our what causes variation in plants, and I'm going to put 0.61. I'll just round up. All right. I'm going to pause from that, and we'll answer these questions in just a second. But what I want to do is I want to show you guys something that has to do with sample size. Okay. So your sample size for your individual data was 20. The sample size for our class data, where we took all the individuals and pulled them into one group, is a lot larger. And why this is important. So if the larger your sample size is, the more reflective of the actual thing it will be. So for instance, if I want to sample Americans and I want to say, hey, what percent of American, I have a hypothesis. My hypothesis is that 100% of Americans are, I don't know, like left-wing social justice warriors. Okay. So what I do is I'm going to go out. I have a hypothesis. I think that's true. I don't actually, but I have a hypothesis. I'm going to go test it. So I go sample 2 people. Okay. I ask both people. I say, hey, are you left-wing social justice warrior? And they say, yes, I totally am. Well, then I take my sample size of 2 and I go back and I write a paper and I say, hey, guess what? All of America is a social justice warrior. And we have an imbalance in our system. Okay. Now imagine I expand that and I say, okay, let's go sample 100 people, not just 2. And I found out, oh, wait, a much smaller proportion of the people are actually left-wing social justice warriors. That's interesting. Okay, so the more samples I take, the more accurate are my statistics going to be. Okay. The outcome of my statistics. So I'm going to do the same thing for this table that I did for this top table. And I want you guys to maybe pause it and do it yourself. It's a good skill to have. If you don't, it's fine. I'll do it for you. But you can pause it and do it and then unpause it and check yourself. Go ahead. Okay, if you unpaused it and you're ready to do this, we'll do observed minus expected for stems. And this is for our class data. And so maybe I'll make a little fancy table like I did for the other one. I'll say, give me some borders. And then I'll say, and this cell is equal to, oh, you know what I didn't do for you guys? Oh, maybe we did do this. I'm trying to think on the other video. All right, let's pause it just for a second. I'm pretty sure this didn't happen on the other video. So you guys can fill this in yourselves. What I did here is I took my total. And to calculate my expected, I took my total, and you can see the formula up here. I took my total, which was 114, and I multiplied it by 0.75, because 75% of my total should be purple stems. And then I took this number, right? So I took the total number, where is that right here? 114, and I multiplied that by 0.25, and that should have given me my total number of green stems that I expected to see. And then I took the sum of those two together to equal 114. And that was my check to make sure that both of them add up to 114. Okay, good. Now that I've done that, I can come over here and say, all right, this is equal to, and I'll give myself 2 parentheses, my observed purple minus my expected purple. And then I'll do my shift 6, which is my exponent 2, close that parenthesis. So just like a scientific calculator, divided by, and then my expected. And I hit enter. Okay. Then I'll do the next one. So that's our chi-squared purple. We'll label that. purple. And then the next one, I'm gonna do the same thing. So I'm gonna say equals two open parentheses, just like a calculator. And I'll say my observed green minus my expected green, close parentheses for that. Shift 6, so exponent 2, close parentheses, divided by my expected green. Boom. And I got my, not purple, but my chi-squared green. And then I'll take the sum of those. So we got to add up for those two categories. So sum of those two. Boop. And then this is my chi-squared. And then what I'll do is I'll just like click on this and I'll bold it so we know that that's that. I already know my degrees of freedom is the same for both groups. And then so I'll just calculate p-value of class data. Okay, so my p-value of class data is going to be equal to my chi distribution. There's my chi statistic, comma, degrees of freedom. Click on that, 1, enter. Uh-oh. It's a little different, isn't it? Notice how the differences between my observed and expected are much greater in my class data than they were in my individual data. So my individual data, my p-value is 0.6. So that's the probability that the differences I saw were due to chance. Pretty good chance that the differences between 16 and 15 were due to chance, and 4 and 5, that's due to chance. So I'm not rejecting my model with this one, with my individual data, but check this out. I go to my class data, which is supposed to be closer, right? It should be a better representation of the actual system I'm investigating. And what did I found? I found my p-value is less than 0.4, 0.04. So that means that the differences I've seen between my observed and my expected are so great that the probability that the differences were due to chance is like less than 4%. So in this case, I can say my model is not accurate and I need to reject my model in this case for my class data. And so I wanted to show you guys that the bigger your sample size is, the more accurate it's going to be about the system you're studying. Okay, so let's go back and finish up the last couple of questions here. Okay, so based on your calculated p-value, and you can use either one, just make sure you specify which p-value you used, whether it was the class data or whether it was the individual data. Was your genetic model and hypothesis supported or rejected? Remember, if the p-value is high, in our case, it supports the model. If the p-value was low, below 0.05, we reject the model because that means that the differences were the chance that the differences were due to chance was very small, and so we reject the model if that's the case. Do you think the no germination numbers, you don't have to answer that, so I'm actually going to get rid of that. Bloop. There is no number 2. Okay. What are 2 challenges you faced during the experiment that were not obvious? How about our plants all died and required critical thinking to overcome? Well, let's think. One of them was the plants died and did very well, and they required critical thinking to overcome. So we had to come up with our own class data. Now, another challenge could be, boy, let's see. Another class challenge could be maybe figuring out which seeds were which. We could say another challenge would be when we were phenotyping our parent A's and our parent B's and our offspring C cups, that some of the offspring in cup C appear to have green stems, even though they shouldn't have. I mean, those would all be good. Give 2 suggestions to future researchers and students conducting this experiment that would help them navigate those same challenges. Well, number 1 would be make sure that your plants get plenty of artificial light, because when they were exposed to just regular sunlight, like indirect sunlight, their stems got too long, they fell over and they died. That was not good. Another challenge that would help them navigate would be, boy, I don't know. Tell you what, check this out. Let's do this. What is one challenge you faced? There you go. You guys can do that. And then give 1 suggestion to future researchers. There you go. That'll make it easier for you guys. You're welcome. Okay. All right, and that's it. So make sure you don't have to print off all the sheets. You don't have to turn in all the sheets. Just the ones that we worked on is fine for this. So feel free to do that. I will see you guys later. Sorry about the double video. Why you have to like watch two different videos for this, but it's the name of the game. All right, we'll catch you on the flip side. See you guys.